Hello everybody and welcome to Newegg TV. My name is Steve and today I'm going to talk to you about SSDs. Alright, so for those of you out there who don't know what an SSD is, it's essentially a flash drive in the size and shape of a hard drive. 2.5 inch is a typical size that you would see for one of these drives, but let's go a little bit deeper than that. Let's talk a little bit about the difference between an SSD and a hard drive. So SSD stands for solid state drive and HDD stands for hard disk drive. Now HDDs, or hard disk drives, are mechanical drives that have moving parts. They have spinning platters and read-write arms that limit their overall performance. SSDs have no moving parts and instead they use extremely fast NAND flash memory to store data. So SSD manufacturers, just to name a few, we have IM Flash Technologies, which is a conglomerate of Intel and Micron, as well as Samsung, SK Hynix, Toshiba, and SanDisk. Those two are both together as well. Now there are several reasons why you might want to upgrade to an SSD or upgrade your current SSD. One of those reasons might be to load Windows faster. With an SSD, Windows 8, and a motherboard with UEFI BIOS, you can experience extremely low load times, around 8 seconds. Games and programs will also load a lot faster. Speaking of performance, performance is typically measured by sequential read and write speeds listed in megabytes per second and random read and write speeds in input-output operations per second, or IOPS. These are the four extreme corners of performance. In a real-world scenario, you'll be doing a combination of all of these things. Sequential benchmark results are typically indicative of large file transfers, or say when you install a program on your operating system. Random read and write benchmarks deal with small file sizes around 4 kilobytes, which is a better representation of day-to-day computing tasks. Now, it's a good idea to research the performance of a drive before purchasing it. We have benchmark results here on our channel, but you can typically read these results right off the retail box, on reviewer sites, the manufacturer's site, or on Newegg's product pages. So let's talk a little bit about the speed at which hard drives currently transfer data. So a WD Black 4 terabyte desktop hard drive has sequential read and write speeds of 180 megabytes per second on the reads and 179 megabytes per second on the writes. For 4K random read and write speeds, we're looking at 400 IOPS on the reads and 320 IOPS on the writes. Now, if I were to speak to you in terms of just those numbers, you can compare the numbers being larger or not, and that's specifically what's going to tell you whether or not they're faster. So an SSD, for instance, let's take the Samsung 850 Pro 128 gigabyte SSD, for instance. It has sequential read and write speeds of 561 megabytes per second and 479 megabytes per second, clearly much faster than the hard drive. Now, looking at the 4K random read and write speeds, we have reads of 97,000 IOPS and writes at 88,000 IOPS. Clearly, the SSD is much faster than the hard drive. Alright, so performance is one thing. Let's talk a little bit about the SSD's anatomy. So we have interface and protocol, and those are two important things I want to make a quick distinction on. SATA is an interface standard as well as a protocol, and you guys are probably familiar with that because most of the drives you're currently using at home are probably SATA 3 or possibly SATA 2. So there's three different revisions of SATA. We have revision 1, 2, and 3, and maximum theoretical throughput is kind of the way we can distinguish between the three of them, and that is the speed at which data can transfer through it at a maximum point. So revision 1 is 1.5 gigabits per second, revision 2 is 3 gigabits per second, and SATA revision 3 runs at 6 gigabits per second. Now another interface is the mSATA interface, and this also uses a protocol for data transfer. It uses the SATA protocol for data transfer, excuse me, but it also has a different maximum throughput. And by that I mean it would depend on the drive that you're currently using because the controller is actually installed on the mSATA drive itself. Now it could be a 1, 2, or 3 revision controller on that particular drive. And what that means is basically it's going to use SATA revision 1, SATA revision 2, or 3 with the exact same limitations on speed. So that's 1.5, 3, and 6 gigabits per second. Now you could also have the M.2 interface, which is something you guys have probably heard of so far, being that Intel has recently released the Z97 chipset, which actually added that. So M.2 has SATA or PCIe protocol. Now SATA uses the exact same throughput as I mentioned before. The flip side of that is that PCIe actually uses a slightly different type of protocol. And what that basically means is that it's going to be dependent on the number and the generation of PCIe lanes that are wired required for transferring data. So for example, PCIe Generation 2 would have a maximum theoretical bandwidth of 4 gigabits per second per PCIe lane, and then PCIe Gen 3 would have a max theoretical bandwidth of 7.877 gigabits per second per PCIe lane. Put that in perspective, if you have an X2 or a by2 Gen 3 drive, that's going to be able to put out around 16 gigabits per second. Now, PCI Express also depends on the number and generation of PCIe lanes, and it's also going to be dependent on what it's wired for. So PCIe Gen 2 would have a max theoretical bandwidth of 4 gigabits per second per PCIe lane, just the same as before. PCIe Gen 3 would have 7.877 gigabits per second per PCIe lane as maximum throughput. Now, SATA Express is brand new, and you probably heard about that as well, also in some of the Z97 chipset boards. It has a maximum throughput of 16 gigabits per second. Also, SSDs have been manufactured to use some unorthodox interface types like USB, Thunderbolt, and wireless. Here's a look at what an SSD looks like on the inside of its chassis. Now we have a PCB, which is the entire green area there. That is the printed circuit board, and essentially it's the wiring that allows connectivity to the other different components inside the SSD. Now we also have the controller. That's a really important part of any SSD. The controller is the integrated circuit that's responsible for communication of data to and from the flash modules on the SSD to the PC, the management of that data, wear leveling, bad block management, error correcting code, garbage collection, on-the-fly compression, and fault tolerance. Now let me just define a couple of those terms for you. Wear leveling is the process the controller goes through by ensuring that all blocks are written to evenly. This way the drive's NAND wears out evenly. Now garbage collection is another important term to define. When a block is marked as erasable, it's not immediately erased. Garbage collection is the process of erasing those blocks and preparing them to be written to once again. It improves the write performance of the drive, and this is what happens when Windows initiates the trim command to the SSD. Now, aside from the speed of the interface and the speed of the flash memory, the controller is a major factor in the performance on an SSD. Now let me just name a couple of SSD controller manufacturers just so you guys are familiar with some names. SandForce, Samsung, Marvell, J-Micron, and SK Hynix, which actually recently bought Link A Media, as well as Indalinks. Now there are some SSDs that actually are designed with DRAM memory for read-write caching, and as you can see in this image, here's an example of one of them. Let's talk a little bit about the NAND manufacturing process. They have 25, 24, 21, and 20 nanometer process that's fairly common right now, with new developments reaching the 19, 16, 15, and 12 nanometer manufacturing process. And all that is just how thin they're getting their wafers in order to compact more and more NAND into the same size chip, resulting in much larger capacity SSD. It's very similar to the way that CPUs are slowly condensed much smaller with their nanometer manufacturing process. So moving along, 3D NAND is fairly new, and you've probably heard about it. Samsung currently manufactures them in 42 nanometer process, and generational in progress is instead measured in layers as opposed to that thickness. The initial vertical NAND started at 24 layers, we're currently at 32 layers, and they're heading all the way up to 48 layer stacks by 2016. So we're going to talk a little bit about some more technical sides of NAND flash, and this is going to bring in probably some stuff you guys may or may not understand, or maybe some things you have or haven't already heard about already. And specifically, we're going to talk about right now the synchronous versus asynchronous NAND. Now, think of these as timekeeping methods that controllers use to keep the rate of instructions executed in sync. They are separated into two regulatory signals, the read events signal and the write events signal. As NAND improved, it gained double data rate, just like DDR did with memory. There was a need to develop a new regulatory signal, and they called that the strobe. It helps the controller cope with high-speed reads and writes. Now, a synchronous device runs its clock for as long as the device has power, just like a clock would. An asynchronous device runs its clock when the host sends the signal for a read or write event, more like a stopwatch. Now moving forward, let's talk a little bit about ONFI or ONFI and toggle, and these are both flash memory standards. ONFI stands for Open NAND Flash Interface. ONFI has several versions or standards. Now, to my knowledge, all manufacturers make ONFI NAND except Toshiba and Samsung. The ONFI standard has alternated between synchronous and asynchronous methods and retains backwards compatibility. Now, each of the ONFI versions essentially differentiates themselves by a max interface speed. Now, here are a few of the maximum speeds that they have achieved, starting with version 1.0. It was starting at 50 megabytes per second. As it improved up to 2.1, they reached 200 megabytes per second. They also added some low-level NAND management tasks like ECC and bad block tracking. As they moved forward to 3.2, it reached 533 megabytes per second, up to 4, and then they hit 800 megabytes per second. Also, they lowered power consumption in version 4. You can head on over to onfi.org for more information on that standard. Now, Toggle 1.0 and 2.0 are two different versions currently available. Toshiba and Samsung make Toggle NAND. Toggle NAND has always been asynchronous. The Toggle DDR 1.0 specification added a DDR, or double data rate interface, to the conventional single data rate NAND architecture. This advance resulted in a 133 megabit per second interface. According to Samsung, Toggle 2.0 NAND has the benefit of reduced complexity and enjoys an increased flexibility in designing smaller chip sizes that brings products to market faster. Toggle 2.0 NAND has a maximum of 400 megabit per second for the interface. All right, so let's talk a little bit about the way that bits or information is stored on NAND, and that is called bit storage technology. Now, one way of looking at data stored in NAND flash is to imagine it represented as small electrical charges being held in a series of tiny NAND cells. Engineers have designed varying levels of storage in each cell, each with their very own advantages and disadvantages. Adding more bits to cells makes it harder to tell which state a cell is in. This, combined with shrinking process geometry, both reduce cell endurance as well as the performance and reliability. With this reasoning, SLC is the fastest, longest-lasting bit technology for NAND flash. MLC is the second, and TLC is the third. So if the performance reduces, why even use MLC or TLC? Well, that's because each increase in bits per cell, the capacity of the overall drive is increased at a fraction of the cost. SLC stands for single level cell, and that is 1 bit of data per cell. Pros: it's the fastest and longest lasting. Cons: it costs quite a bit more than MLC and TLC. Also, they are typically much smaller capacity drives than the other two. MLC stands for multi-level cell. That means that it's 2-bit MLC, and it also has 2 bits of data per cell. Pros: more capacity and less costly than SLC. It's the happy medium. Cons: slower than SLC and lower lifespan than SLC. Now, TLC stands for tri-level cell. It's a 3-bit MLC, and that means that it has 3 bits of data per cell. The pros: it's the most inexpensive and most capacity per cell compared to the other two, and it's still faster than a hard drive. Cons: it's the lowest lifespan of the three, and Samsung states it can take up to 4 times as long to write and up to 2.5 times as long to read 3-bit MLC NAND than it does SLC NAND. Now, let's talk about the new kid on the block, 3D VNAND. That stands for 3D Vertical NAND. Samsung pioneered this technology, which is essentially vertically stacked cell layers of NAND. Samsung's first design was a 24-layer cell array structure of MLC 2-bit NAND. The second generation utilizes 32 layers. Pros: a ton more capacity, twice as fast as 2D planar NAND, and that is basically what standard NAND is called because now we have 3D. They also have 10 times the cell endurance than SLC memory and 46% less power consumption. Cons: pretty much only the price on smaller capacities might just be a little bit higher than normal. We can deal with that. Also, we have another brand new version of 3D NAND. They're calling it 3-bit 3D VNAND, or TLC 3D Vertical NAND. Mass production of 3-bit VNAND flash started in October of this year. They utilize a 42nm process technology with 3-bit multi-level cell wafers stacked vertically. These new chips will likely have less performance and reliability than the original 3D VNAND, but the capacity skyrockets. Who knows what the future holds? We may see full replacements of hard drives with these super large NAND packages. Now let's talk a little bit about durability. Program and erase cycles, for instance. It's another important aspect of NAND. Each block has a finite number of times that it can be written to. The controller keeps track of these program erase cycles so that it knows when a block is no longer usable. A drive's lifespan is determined by the amount of times the NAND can be written to in program erase cycles. But instead of PE cycles, most SSD manufacturers have moved to a new metric. This can also be displayed as the number of gigabytes written per day over the course of the warranty. Over-provisioning is the practice of allocating an additional amount of NAND with the purpose of increasing SSD performance and endurance. As the blocks go bad, new untouched blocks are pulled into use from the additional allocated NAND. In this section of video, we're going to move on to installations, and in front of you I have an MSI gaming laptop. Here you can see where the 2.5-inch drive would go in, and in this particular case it's a standard hard drive. If you wanted to replace this, you absolutely could. Just make sure that you check out your warranty information and make sure that by opening the back of your laptop you're not actually voiding any warranty, or if you are and you don't care, then please continue. Otherwise, you're definitely going to want to make sure that you don't have any static on your body, so you want to make sure that you touch something like a ground that actually grounds you. If you want to be extremely careful, you can get an anti-static strap which actually wraps around your wrist and then attaches with alligator clips onto something metal inside. Make sure you are definitely touching something metal, like this heatsink would probably be one option. Ideally, in a case, you'd actually have a ground. So moving forward, as long as you're completely out of any kind of anti-static electricity or any kind of static electricity, we're going to move forward into the drive. So you'd remove this by finding the two different screw holes that would be here, remove both of those and slide it out. I'm actually not going to show you this because this is fairly straightforward, although SATA drives might be a little bit more difficult. Alright, and as you can see on this particular motherboard, we have two different SATA ports that we could actually use, and take a look at the user's guide to know which one you want to start with. In this particular case, we're going to use this port here, and the way you want to install them is by first, well, I have the drive here, but by first removing both of these screws and then sliding the drive in. And it goes in slightly at a 45-degree angle here. Let's see if I can get it to line up. I have to make sure that it lines up with the teeth down here at the bottom. So you can see there's a shorter area and a longer area, and these teeth have to line up. So just like this. See, it kind of pops up a little bit. What you do is you press it down and then apply both screws, screwing them into each of their individual holes. And as you can see, both screws are screwed in and this drive is essentially installed. Now if you're going to use this as an extra cache drive, you can do so. I would recommend probably installing your Windows operating system directly onto this. It's going to improve performance. Alright, this is a Z97 motherboard. Specifically, it's the ASRock Z97 Extreme 6. And if we take a closer look here, we have ASRock's Ultra M.2 port, which is basically an M.2 port, but they wired it up to be PCI Gen 3 by 4, which basically means it's going to get 32 gigabit per second throughput, which is insanely fast. Depending on your drive speed, that will not be a bottleneck most likely. So installing this M.2 drive is pretty much the exact same way we do the SATA. It's going to slide in here at an angle. If I can get it in there, get in there. Actually, not at an angle, a slighter angle than before. So it's got a little bit of a pop-up here, and then making sure that this is lined up exactly where your drive needs to be. Otherwise, you're going to need to unscrew that thumb screw and move it exactly where it should be. Then you just take one of the screws that comes inside the box and screw it in right there. Now the SATA Express connector would actually be plugged in here with these three plugs actually making up one port. Plugs in directly there, and then one into the other side where the drive is. Unfortunately, I don't have a SATA Express drive to show you, but essentially it works the exact same way as installing a SATA drive. Alright, and now we are looking at the Gigabyte G1 Sniper A88X motherboard. This is, of course, an FM2 Plus board. It has the PCI Express slot that we're going to need for this installation, as well as SATA ports. So here is the AMD Radeon SSD that I have in front of you. Now, of course, you can take this and use the adapter here if your case doesn't actually have any room or any slots that you can use for 2.5-inch drives, but this 2.5 to 3.5-inch adapter will actually allow you to plug it in or install it into one of the 3.5-inch drive bays that are there in your system. Now, the SATA connector interface is here on this edge, and you can see it's two different L connectors. The one on the right here is for data that goes to the motherboard. The one on the left here is going to the power supply and providing power for the drive. So we'll start first with this SATA connector. So I'm going to go ahead and pop this in for you, show you how that goes in. I'm going to push in nice and firmly, but not too hard because you can break that clip right off. Now here is the other connector, that's for power. We're going to go ahead and slide that in as well. Now I like to use these adapters because essentially I can use a single cable straight from my power supply to go in 4-pin Molex, so I can just use that for powering everything. But you could also use just the standard SATA connectors that are already there in your power supply as well. So you're going to need to plug this into your power supply to give it power, and on the other end you're going to need to take this and plug it into the motherboard. So you'll do that by taking the L connector, taking a look at it, making sure it matches up with the one here, and plugging it directly in to the board. All right, now finally we have the PCI Express card style SSD interface installation, and for this we're going to use the Asus Raider Express for that. Now there's obviously plenty of different options out there, but this is pretty simple on how to install it. Just make sure that you know exactly what the PCIe lanes that are actually going to be in use, and make sure that you don't pick one that doesn't work. For instance, you don't want to put this in a PCIe X1 or by 1 slot if this ends up being a Gen 2 by 2. So keep that in mind. I'm using one that has 8, so we have plenty of lanes and it's only a by 2. So I go ahead and slide it in. That's pretty much it. Put the screw inside where your chassis is and it's installed. Well, all right, everybody. Thank you so much for watching this video on SSDs here on Newegg TV. If you like what you saw today, don't forget we also have a YouTube channel. That's at youtube.com/Newegg. And until then, we'll see you guys very soon.